Okay, thank you for this. I'd like to talk to you about collaboration and innovation, but to also take a step back and maybe away from the Earth and try to convey to you the notion that we might be living in a universe that is maybe different from what you are hoping that it could be, and certainly different from what I thought the universe was like when I was growing up. But let's start with the first picture. And do I have control of that? Okay, yes. All right, this is the surface of Mars. It was taken just a few days ago, really. And it, I think, is an amazing landscape. It looks eerily like the Earth, but of course it's a different world. The atmosphere is actually very thin. You cannot breathe it. It's made of carbon dioxide as well. It's very cold. Average temperature is minus 60 degrees centigrade. And to make things worse, it's an extremely oxidizing surface environment, and meanwhile we want to go there. The reason why we want to go there is because Mars has had a long history involving liquid water near its surface. And on Earth, everywhere where you've had liquid water, you have life. And every form of life that we know of on the Earth requires liquid water, even in deserts. Liquid water doesn't have to be there all the time for that life, but it has to be there sometimes at the very least. And so we're fascinated by this place because we might find some answers to some fundamental questions, including the notion of whether or not we are alone. But to get to Mars and to work there, you need a spacesuit. And the challenge that we face is that we have to reinvent the spacesuit to go to Mars. And here's why. This is the state-of-the-art in spacesuits. It weighs 140 kilograms on the Earth. Now, of course, when you are in low Earth orbit at the space station or on board a space shuttle, for example, it's weightless, essentially. When you go to the moon with the thing, it has a felt weight of about 25 kilos, so it's quite manageable. And this is why you could see the astronauts on Apollo hop around. But if you take this spacesuit to Mars, even though gravity at the surface of Mars is 38% of what it is on the Earth only, this spacesuit would have a felt weight of about 50 kilos. Okay? So it's way too heavy for you to be an effective explorer. So the challenge that we face before we're ready to go to Mars is to cut the mass of this spacesuit in half. And that is going to require some reinvention of the spacesuit. So here's what we did. We have been working over the past few years with engineers who were thinking of how do you really reduce the mass of this spacesuit, but who didn't necessarily have the background or the experience with doing geological fieldwork. And then we paired up these engineers with people who actually do geological fieldwork in deserts, where they actually use vehicles to roam around and cover great distances. If you do geological fieldwork in places where you have a lot of vegetation, you would not use an ATV. But if you're in a desert, you realize that an ATV is a good solution to moving around. And then, of course, we also go to a place where we can partner with people who do robotics, because the idea, of course, is that if you're exploring Mars, you're going to want to have some aspects of your vehicle or spacesuits that will involve robotics. You put all this together in a pot, you stir it, and you come up with essentially a reinvented spacesuit. And the solution is, the most heavy part of your spacesuit is your oxygen tanks. And what you want to do is actually offload your spacesuit of the oxygen tanks. You want to put the bulk of your oxygen tanks on your ATV, on your rover. And so the new exploration system that we anticipate we'll be using on Mars is a spacesuit whose mass is reduced by other clever ideas as well, like different materials, but fundamentally by offloading the oxygen tanks onto a personal rover, an ATV. So every time you're exploring Mars, you would connect your backpack to the oxygen supply of your rover, and then when you need to step off and go chip away at rocks, you will have just very small tanks in your spacesuit. And what if you run out of oxygen? Well, you won't risk that because your ATV will be a robotic ATV and it will follow you very closely. So you will always be within close range of your vehicle. But where we really want to go is not just the surface of Mars. to find life, to have a chance of finding extant life on Mars today, life that is really still alive potentially, we want to go into the subsurface. There's no liquid water today at the surface of Mars, at least not in any durable or reliable way. However, at depth, the story could be completely different. Anywhere from a few hundred meters to 1 to 2 kilometers of depth on Mars, we have to have liquid water because there's so much ice on the planet. And the challenge, of course, is that, and part of the reason why I've been coming to Stavanger is to look at what the state of the art is in drilling. And if you think conventionally at how you do drilling, you are faced with this massive problem of having a lot of equipment to get to Mars, to do a normal deep drill hole and somehow reach the water and sample it and explore it for life. But we've been collaborating with a company that has had a very innovative idea called ZapTech. ZapTech. ZapTech has come up with this very exciting and novel approach to drilling, which is to use plasma physics. And rather than having a long drill train, you have essentially a drill head that is delivering high energy density of plasma into the rock. It shatters the rock. It's the result of a collaboration between plasma physicists with electrical engineers who also are working with folks who have extensive experience in drilling. So this collaborative environment has come up with a practical solution for plasma drilling into rocks. And all of a sudden you have cut back on the amount of mass that you need to take to Mars because the real link to the surface between your drilling head and the spacecraft is a cable that's delivering the power. And also you're using carbon dioxide, compressed carbon dioxide as your drilling fluid. You don't have to involve liquid water. NASA's interested in this. Our Mars Institute is also collaborating on this. And the hope here is that with ZapTech, we're going to come up with a practical solution to actually reach the subsurface of Mars down to the liquid water. And I hope you share with me the excitement of this. I had always thought that finding life on Mars would be something left to future generations. But as it turns out, it's something that we could see actually happening within the next couple decades, maybe. And not only that, but some piece of hardware developed in Stavanger could be the first piece of hardware created by humankind to encounter alien life. And I think there's something that goes beyond the ambitions of any space agency in that possibility. So beyond this, I am wondering about our position in the universe and this whole business of whether or not we're alone. And you will see that this is also something that can be answered perhaps through collaboration. This is the Andromeda Galaxy. It's located 2 million light years away. It's about 100,000 light years across. It's in some sense a mirror image of our own galaxy, the Milky Way. And I grew up thinking that there might be many alien civilizations out there. Okay? But the formula that really allows you to estimate the number of civilizations is this formula called the Drake equation. And you don't have to memorize it, but you should know simply that the number n here represents the number of intelligent civilizations in our galaxy. And it's a simple formula. It's the product of 7 terms. And the big challenge, of course, is that we don't know the exact value of each one of these 7 terms. And so there are big question marks on them. But if you knew the values of these 7 terms, you would have the answer. You would know how many alien civilizations there are out there. But we made a lot of progress, in particular through collaboration. Each one of these terms is addressed by one or several fields of research that are familiar to us. Astrophysics and cosmology, the search for extrasolar planets, planetary science, paleomicrobiology on Earth, evolutionary biology on Earth, anthropology, history and sociology. All of this expertise collaborates together to quantify these terms in hopes of giving you the answer n. So let's look at the state of the art of this formula. R substar is the rate of star formation in our galaxy today. Okay? And this is a star-forming region seen from Hubble. We didn't know the answer to, or the value of R substar over the past decades, but we now know it. It's about 20 to 50 stars per year throughout the galaxy on average. Okay? That's a very important number because the uncertainty on it is fairly small, and it's something that really constrains the beginning of this formula. The second question that we have has to do with the fraction of these star systems that have planets. And nowadays, we are discovering more and more planets. There are over 1,000 planets that have been discovered by the Kepler mission. These are planets around other stars. And so this term F sub p, which is, again, the fraction of stars that have planets around them, still theoretically has a wide range of possibilities, between 5% and 100%. But the uncertainty has more to do with the fact that we've been limiting our search to certain types of stars and also certain sizes of planets. But among the stars that we've been looking at and among the planets that we've been able to detect, the yield is approximately 50%. So about half the stars out there, the ones that we've looked at so far, are yielding planetary systems around them. So this is a formidable increase in our chances of finding life out there. Within a planetary system, how many environments are there that are suitable for life? And by that we mean an environment that has liquid water, energy, and nutrients for life. So one way to look at this is to examine what's called the habitable zone around a star. This is the sun, and the habitable zone, again, is the zone where temperatures in particular are sufficient for, or adequate for liquid water to be present. And in our solar system, the habitable zone would include about 2 planets, planet Earth and planet Mars. Okay, this is a sort of a temperature gradient issue. Too close to the sun, water would vaporize. Too far out, it would turn to ice. But for stars that are smaller, which are more common than the sun, the habitable zone is smaller. And the most common types of stars, the M-class stars, which are about 1/10 of the solar mass, you really have a very small habitable zone. But N sub E for the solar system is 2, based on this basic habitable zone concept. And it might shrink down to 1 planet, or none, in fact, when it comes to smaller stars. But there's a caveat. The sun itself, for one thing, is not constant in size. Right now, it's much smaller than the orbit of the Earth, but in about 4 billion years, it's going to turn into a red giant. The orbits of Mercury and Venus will be completely engulfed in the sun, and the sun's surface will be right there next to the Earth. In case you have long-term investment plans, you should consider them to be adjustable. The other caveat to this issue is the fact that the possibility of life, of liquid water, is not only dependent on how far you are from the star. We have life that is thriving at depth inside the Earth in environments that have liquid water, but that are completely independent of our proximity to the sun. And in fact, if you look at where in the solar system we have liquid water today, you will find that there are actually 8 or 9 environments where it is present. It's present inside the atmospheres of Jupiter, Saturn, Uranus, and Neptune. It's on the surface of the Earth and inside the Earth. Liquid water is present at depth on Mars. It's present at depth on Europa, one of the moons of Jupiter. And it's present at depth on Enceladus, an icy moon of Saturn. Okay. So in our solar system alone, N sub E is anywhere between 8 and 9. So in principle, it could be a very small number if there are many small stars, like the M-class stars, or up to 10 perhaps as a sort of a representation of how many there are in our own solar system. So I'm going to submit to you that we should pick n equals 1 as a reasonable but somewhat optimistic number. And I'm not concerned about being optimistic because, as you'll see, this is something that will still result in a puzzling outcome. The fraction of planetary systems where there are environments suitable for life, where life actually appears, is a number between 0 and 1. On Earth, life appeared very early, and this is one of the earliest life forms we have a record of. But we don't have any trace anymore, any fossil record of the very beginnings of life on Earth. And this is why we're so interested in Mars. Mars actually offers us an opportunity to really examine several key possibilities. Life could have started on Earth, and of course blossomed on Earth, but also expanded to Mars, because these planets are not closed systems. We know today that we have meteorites that have come naturally from Mars to the Earth. Mars gets hit by asteroids and comets. These impacts eject rocks from the planet. They drift through the inner solar system. They fall onto the Earth. And similarly, there must be Earth rocks today sitting at the surface of Mars that have been ejected from the Earth and travel all the way out there. So life could have started on the Earth, led to us, but also generated a branch of cousins of ours on Mars today. The converse is possible too. Life could have started on Mars and come to the Earth. We are also possibly facing the possibility of finding life on Mars that had an independent start of life on Earth, in which case we would really be dealing with an alien form of life on Mars. So what's at stake in our search for life on Mars is really the possibility of answering some of these questions and deciding between these options. So F sub L, the fraction of stars where life actually appears, or planetary systems and environments that are suitable for life where life actually appears, is in principle a number that could be anywhere from being very small to 1, but we have a clue in our own solar system. In spite of the fact it's the only example we have, the key clue is that life appeared very early in the Earth's history. It looks like it was an easy process. Okay? The Earth formed about 4.6 billion years ago. We have signs of life at about 3.9 for sure in Earth rocks. And so I will submit to you that F sub L, even if it's a bit optimistic, that's okay, is 0.5. Okay, 1.5 of environments that are suitable for life, you actually see life begin. But what about life that evolves to intelligence? This is a vertical column representing the entire history of the Earth. It formed 4.6 billion years ago. The present is way up there. Okay, this is the earliest record of life at about 3.9. Well, all the dinosaurs was in that Mesozoic area, okay, in the green up there. The bulk of Earth's history has only known relatively simple and primitive forms of life. Complexification really happened at the time of the Cambrian explosion about 550 to 600 million years ago. If you blow up that final section, that the final 600 million years, the latest 600 million years of life on Earth, you can see that this is when it was all happening. The first fish, the first land plants, the first amphibians, the dinosaur era. Homo, okay, us, or at least the close relatives that we came from, essentially showed up only about 2 to 3 million years ago. All right? So we're a very late event in the history of the Earth. To the extent that F sub L might be a number that's closer to 0.002. If you look at our presence on the Earth in relation to the age of the Earth, okay, we are down there at the 2 chances per 10,000 level. If you were to visit the Earth randomly at any point in history, of its history, there's only 2 chances in 10,000 that you would run into something that looks like humanity. Okay, the rest of the time, we are out of the picture. So what about this intelligent form of life turning into a civilization? Well, that is defined as a society that all of a sudden is able to come up with and use Maxwell's equations, which are shown here. It's the ability to use electromagnetic waves to communicate with other societies in space. Well, that capacity happened relatively shortly after the emergence of intelligence, within a couple of million years. And so, again, the suggestion here is that this was something relatively easy, although it shouldn't be an obligatory outcome of 1, mainly because there are caveats. You can imagine intelligent societies being born on planets that have a permanent cloud cover, or they are living in oceans where you really would not have much use of electromagnetic waves. So I would submit to you that F sub C, optimistically still, could be maybe at the 10% level, 0.01. Finally, the last term is the longevity of a civilization. There are many things that threaten our longevity. This is our population curve in blue up to the present. We're currently at 7 billion people on our planet. These are 3 different outcomes that are considered by the UN as being possible in our future. So there are cases of population explosion that could really be a threat to our long-term survival as a society. We are also subject to the threat of impacts, which we can do something about. We are also, of course, subject to the vagaries of world wars, and we're certainly concerned about that too. Historically, cultures have lasted 500 to 5,000 years or so. And so In our case, we've been capable of communicating with alien civilizations only for about 100 years. And I think, optimistically, we could give ourselves up to maybe 10,000 years, but there's really no basis to believe that we could be surviving as a society well beyond that. I mean, we could, we hope to, but it's already a pretty large number. So here's the final outcome. If you're optimistic, if you've used the numbers that were on the best end of things throughout the talk, you might come up with a number n of 50,000. Okay? We could be one among 50,000 intelligent societies in our galaxy today. This would mean that the nearest civilization might be a few light years away. If you use the most pessimistic numbers in this discussion, you end up with something that makes us exceptionally rare. We are essentially completely alone. And not only that, we happen here because we're not the product of very simple processes that are reproducible elsewhere. In my humble opinion, and these are the numbers that I've been using, you end up with an incredible outcome. And remember that my numbers were already quite optimistic. Okay? They were within the brackets of reason, but they were quite optimistic. We're still only at n equals 1. And so this, I think, has a profound potential implication, which is there could be one other civilization out there in our galaxy right now. Its average distance might be 50,000 light years, because our own galaxy is about 100,000. Or we could be it. Okay, we could be it. And this, incidentally, would answer the Fermi paradox. Enrico Fermi, who won the Nobel Prize, came up with a discussion. And his concern was, if there's so many galactic civilizations out there, how come we don't see them? Okay? And the answer is possibly because n is a very small number. So this possibility, I think, has several quick consequences. One is that we're profoundly alone. It's sort of eerie how lonely we are in this galaxy. Number two, it should give us a sense of responsibility. This is a planet we should love, and we should treasure the fact that we are humans and have achieved this kind of advanced stage of evolution. And so, if anything, it should give us a sense of respect for human life. It doesn't mean, and that's the third consequence, it doesn't mean that there's no life out there. There's plenty of primitive life. We might even find microbes in the solar system itself. There might be fishes in oceans on planets within about 100 light years. There might be dinosaur type of animals on planets about 1,000 light years out, because dinosaurs have been around for so long. There might be even primitive intelligent beings, more or less like ourselves in terms of capability, about 10,000 light years out. But intelligent societies like ourselves, very rare. So with that, thank you.